Uh, Hopefully, I gave you the practice in the last lab time. So I hope some of you already finished that. Okay. Yeah. Well, once again, those are very good and important review for your class. Okay. So if you can work on those practice, that's going to be very, very benefit for your exam. Okay. And once again, this Thursday, I'm going to open the take-home exam, which is on the Canvas. Okay, I will put that in the first module of your class. Okay, so you should be able to see it very obviously. Okay, all right. So let's start to review our class. Okay, last time we talked about the three concepts. The first concept we talked about is the formal charge. You remember still formal charge? Again, the formal charge is not talking about the charge of the compound. Okay, we're not going to figure out the charge of certain compound. We just try to figure out whether what kind of structure is correct or not. Okay, so we talk about, I mean, if we base on the rule for the Lewis structure, the CO2 can write the Lewis structure like this, or they can write the Lewis structure like this. But which one is the better Lewis structure? Okay, or which one is the correct Lewis structure? We don't know if we just base on the octet rule or duet rule. Okay, so those are all have the same Lewis dots shows in the structure, but one has a triple bonds, a single bond, one has two double bonds. Which one is correct? Okay, then we need to use informal charge to determine what is exactly the formal charge for each of the compound, each of the atoms. As long as the atom has a zero, the more zeros, the better. This is our conclusion, right? For the compound, the more zeros, the better. So if you're the formal charge, generally the equation is just the number of the valence electron for these elements, subtract the total number of bond, and plus the total number of the electrons not in bond, okay, which is the dots alone outside. And then you can, based on this, you figure out, okay, so this guy has a 6 valence electron, subtract the 2 bonds around oxygen plus 4 dots, which is 0. So this oxygen is 0, this oxygen is also 0. And this carbon, you see, that's a 4 valence electron, subtract the 4 bonds, and no lone pair, no electrons outside, which is also 0. So you got all the 0 for the CO2, oxygen and carbon. But if you calculate this one, you figure out the carbon inside is 0, but this oxygen, they have a 6, subtract the 1 bond plus 6 dots. So you got a -1, and this you got a +1. So those are not equal to zeros. So that is why we talk about this kind of the structure is more better than this one, right? This is the purpose for the formal charge. Again, formal charge is not used to helping figure out what is the charge for those atoms. Okay, it's just a way helping you to determine which structure is correct or not. Okay, so this is a formal charge. And we also talk about the polar and the non-polar by definition, right? Polar, so what is the polar? What is the non-polar? And we talk about non-polar is easy to determine. As long as this bond, which one is a polar bond, which one is a non-polar bond. The polar bond, that means this guy is a polar bond, or is a non-polar bond. That because, I mean, those bonds, the electrons in the middle is not moving to any side. They're just right in the middle because on the both sides, they are identical atoms. So the electron negativity power on those two atoms are exactly the same. So the electrons in the middle, the shared electrons not going to anywhere. But for the polar molecules, it's because they have the difference of the electron negativity for different atoms, hydrogen and chlorine. Hydrogen is more stronger than chlorine is more stronger than the hydrogen. So chlorine is going to pulling the electrons more towards to it. And in another word, the hydrogen gonna have a less share with the shared electrons. Well, if we talk about this situation has a 50-50 sharing for the electrons, but in this case, it's not going to share 50-50 sharing. Maybe they have a 90-10 sharing of the electrons. I'm not sure, I just give you one example, which means make the shared electrons more close to the chlorine, and the chlorine side will have the partial negative, and the hydrogen side will have the partial positive. And the reason we call it is a polarity or polar, that means in the whole molecule, in this whole molecule, on the chlorine side, they have a positive charge, a negative charge, partial negative charge. The other side has a partial positive charge. The difference of the charge make this molecule polar. Okay, just like the difference of temperature make we have the equator and the North Pole, South Pole. That's it, right? So polarity is just talk about separation, the separate the two extreme things. Okay, so that's why we have a polar molecules, a polar bond in these cases. And we talk about there's another name. So we call this guy has a polar molecule, and we can call HCl bond is a polar bond. And we can also call HCl bond has dipole moment. So polar dipole moment, that means we have the trend from one side has a more negative charge, the other side has a more negative, a positive charge. This is called a dipole moment. So we have the trend, the electron shift from one side to the other side, and this is called a dipole moment. In other words, dipole moment just means polar molecule or polar bond. Okay, so dipole moment just means polar bond or polar molecule. Are you clear? Okay, so this is another way to talk. This guy is a polar. Are you clear? Okay, so this is what we talk about, and we talk about. Generally, we're determining whether it's a polar or non-polar. We determine based on the difference of the electron negativity. So based on the electron activity, the two molecules, if they have a bigger difference of the electron activity, then they will have a more polar bond. Okay, they will have a more polar bond. So that is why, based on the periodic table, if we have a hydrogen over here, we have a carbon, and we have a nitrogen and oxygen, and you can see, okay, so what is the difference between carbon-hydrogen bond, nitrogen-hydrogen bond, and the oxygen-hydrogen bond? We see those are the different elements with the hydrogen bond. So those bonds, which one is the strongest, has a stronger polar bond? Which one is a more polar, or the most polar bond in those three? Well, then you just need to look at the difference, the electron negativity difference, right? So hydrogen and the carbon, the difference is over here. The hydrogen and the nitrogen difference is over here. This is a carbon, hydrogen. Carbon, nitrogen is over there. And the carbon, hydrogen, or oxygen and hydrogen is that much. So which one has a bigger difference? Obviously, oxygen and hydrogen has a bigger difference. Then obviously this guy is the most polar bond in those three, right? So this is generally we talk about based on the periodic table, you can determine the strength or the polarity of the bond, okay, in several bonds, right? This is what we talk about. And last time, the last concept we talk about in the last time, which is the geometry of the molecule, right? Geometry of molecule. And we talk about the, there's a model, it's called the VSEPR model. It's called the valence shell electron pair repulsion. So the repulsion actually is the most important term in this, right? We talk about the reason the molecule has a shape. It's because they are the electron cloud is occupied space. So we have a central atoms here. The central atom, on the outside of the central atom is not nothing. It's occupied space by some of the electron cloud, occupied by some of the electron cloud. And the different number of the electron cloud will give it the certain shape because the cloud will repel to each other. So they have to form a certain way to make the energy, lowest energy, make this stable, make this form stable. So that is why we need to, as long as we determine the different number of the electron cloud, we generally can figure out what is the shape of those molecules, right? And we talk about if we have a in the around the central atom, if we have a 2 electron domain, and we talk about what exactly electron domain. Electron domain could be single atom, single bond, double bond, or triple bond, and plus another one, which is electron lone pair. Those are all can count the electron domain, okay? So here I need to be clear, okay? So how do you count? For example, if we have a carbon, and this carbon has 4 single bonds around it, and just this is based on the Lewis structure. You can look at the Lewis structure. Central atom carbon, if they have a 4 single bonds around it, and then we call this central atom has a 4 electron domain because they have 4 central atoms. They have 4 single bonds. Okay, yeah. But the carbon can also have 2 double bonds, right? If the carbon has 2 double bonds around it, and then please, the 1 double bond count only just 1 electron domain. It's not count to 2 electron domain, okay? So in this case, the carbon only have a 2 electron domain in these cases, right? So they have a central atom, but they only have a 2 electron domain around it. But the carbon can also have, for example, they can have 2 single bond and 1 double bonds also. But in this cases, this carbon central atom, they have a 3 electron domain. They have 2 single bonds, which counts 1 electron domain and 1 double bonds. So this guy has a 3 electron domain. That makes sense, right? Well, the carbon can also has like 1 single bond and 1 triple bonds. And in this case, this carbon will have 2 electron domain. But triple bonds also count 1 electron domain, okay? So double bonds, single bonds, and triple bonds, they are all count one electron domain. So this guy has a 4 electron domain. And the reason we need to count the electron domain is because we need to, based on the electron domain, to figure out the geometry of these molecules. Okay, yeah. This has a 2 electron domain. They have 3, and this is also 2. And so another case is like oxygen. Okay, oxygen, they could have something like this. Okay, so this oxygen could be like this, and they have 2 lone pairs and also 2 single bonds. Again, we talk about electron domain, also including the electron lone pair, which means this guy has 2 electron lone pair. They count 2 electron domain, and 2 single bonds count 2. So around oxygen, this guy also has a 4 electron domain. So this guy also has a 4 electron domain. And oxygen can also have something like that, right? 2 lone pairs and 1 double bond. So in this case, this oxygen has 3 electron domain. Okay, yeah. And the oxygen could also, but very rare, could also has something like this. And this count 1 lone pair and 1 triple bonds. So this guy also count as 2 electron domain. Are you clear? Okay, so this is how we determine the electron domain. Okay, so if we have a 2 electron domain, the electron domain geometry usually is a linear. Okay, which means they only have 2 lines, just 1 line, which is like this, right? So this guy, if we write electron domain, this is a linear shape. It's just linear. It's a line. Okay. But if you have a 3 electron domain, that's gonna be so linear is a central atom around it, then it will be like this. 3 electron domain, then we have a central atom, and we have 3 side atoms. Then it will like this. This is called the trigonal planar. Trigonal planar. The reason it's called a trigonal planar is because this is triangle. So you look at this. This is a triangle. You see they have 3 angles, and those electron domain will going to repel to each other's. So make those identical. And the bond angle, you talk about the bond angle over here, that's going to be 120 equally. And the reason it's called planar is because those atoms are in the same plane. So that's called the trigonal planar. Okay. And if we have a 4 electron domain, then if we have 4 electron domain, then this guy is more complicated. We call this is a tetrahedral. Tetrahedral. So you have a central atom, 1 stick out, 1 is go that way. And but there's another 2. Another 2 actually is not in the same plane. 1 is a stick out. We're using wedge to represent. And the other is sticking in. We're using dash to represent. So if you learn organic chemistry in the future, the student we want you to draw a 3D in 2D paper. Okay, so generally we're using wedge and a dash this way to draw. So the wedge is 1 pointing out, the dash is 1 as a stick in. Okay, so those are the different. So this is called a tetrahedral. The reason it's called a tetrahedral, that means this guy has 4 faces. Okay, tetra is 4, hedral is a face. Okay, tetrahedral is 4 faces. Right, so if you have 1 more dots, then this is not 2D, it's a 3D. Okay, so now it's something like that. Then you can see, okay, 1 is a sticking out, 1 sticking out, 1 is a sticking in. Okay, so the bond angle over here is not 120, it's not 90, it's something in between. It turns out it's 109.5. Okay, it's 109.5. So this is a 4 electron domain. And can we have the 5 electron domain and the 6 electron domain? Yes, we can. So I'm going to give you a video so you can look at it. It's more straightforward. And this is also a balloon demonstration. Okay, let's see.
Degrees. Now, at this point, I'm going to pop one of these balloons just to get it out of my way. And we're going to talk about what happens if we go on from AB4 to AB5. If you can put 4 things in a molecule, can you put 5? Well, let's just see. And we're going to color coordinate this by putting a different color in here. I think the color coordination helps the students to be able to visualize what we're going to look at here. So we're back to the tetrahedral 4 things, and now we're going in for AB5. The 5th one is we twist those balloon necks into the center, and we end up with something that looks a little bit like this. This is the shape. Again, A is in the center, and now we have 5 different atoms, all alike, so that we have an AB5 molecule here. But with this AB5 molecule, we have 2 different kinds of geometries taking place. We have the molecules, which are the red ones, and as you can see here, are located around what we would call the equator of the molecule, and they're called equatorial positions. And then we have the yellow balloons, and here's where the color coordinating helps. The yellow ones are called the axial positions. And so we have combinations of 90s, 180s, and 120-degree angles in this molecule. And that becomes important when you begin to go into your advanced classes or your AP/IB classes, because there's where you can begin to talk a little bit about some of the geometries and the shapes that are taking place there. So the students want to know, okay, we can have 2 things, 3 things, 4 things, 5 things. Can you have 6 things around a central atom? So yes, and we're going to pop another balloon now. Get rid of it. So we're back to our tetrahedral shape at this point. And we're going to go to a slightly different color, just because color is fun. We've got back to 5 balloons. Now we're going to 6. And if I can get all of this oriented properly. If I can get all of it oriented properly. Maybe I can get all of it oriented properly. There, success. Now we have 6 things covalently bonded around one central atom. Again, A, the central atom buried deep in the center. B, 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 and B. And with this shape, what we have is all spots are filled. We have 90-degree angles, every direction in here. And this is the most atoms that you will typically find around one central atom because of the geometries. And in order to make this happen, the central atom A would have to be a relatively large atom so that we would then have relatively small atoms bonded around that. The analogy I make is it would be difficult for 6 lions to drink out of one small bowl of milk. So if the central atom in the middle here is a small atom, this would be a difficult geometry. On the other hand, if I have a wash tub full of milk, 6 kittens could drink easily from that. So if the central atom is very large, then the corresponding atoms around the outside make that happen very nicely. And this shape is called octahedral. I failed to mention on the previous shape that we had was called trigonal bipyramid for the AB5. And this shape then would be called octahedral. And the reason it's called octahedral, you think octa, 8, well, you only have 6 things bonded. But if you look at it, these 3 balloons form one face. These 3 balloons form another face. So I have 1, 2, 3, 4 faces on top, and I have those same 4 faces below, giving me 8 faces, and therefore the octahedral name for that. The color.
Okay, so this is generally, we have 2 more things over here. So if we have a 5 electron domain, in this case is the geometry for the electron domain geometry. Electron domain geometry, that's called bipyramidal. Okay, so it's called a trigonal bipyramidal. Trigonal bipyramidal. Okay, I know this one is pretty long. Okay, so generally it's a structure like this. We have a central atom over here, and we have a two straight line. And one is this guy still in the same phase in the plane, but we have two more. One is sticking out, the other one is pointing in. Okay, so now this is called a trigonal bipyramidal. The reason it's called a trigonal bipyramidal is kind of like we have one pyramid on the top, and there's another pyramid in the bottom. So there's a two pyramid over here. And the reason it's called the trigonal is because the baseline over here only just the 3H of here. So that's why it's called the trigonal bipyramidal. So two pyramid, but this is a trigonal pyramid. Okay, so so that's why this called trigonal bipyramidal. And the last one, if we have a 6 electron domain, then this guy is called octahedral. Octahedral. Octahedral is we have a central atom and we have a 6 side atoms. One straight line, another straight line, and in this case, 2 sticking out, 2 atoms sticking out, and 2 atoms pointing inside. Okay, so now this is the octahedral shape. That's octahedral shape. Okay, so now we talk about those electron domain geometry, and this is, those geometry is fixed. If you have those domains, you have to have forming those kind of shape. Okay, but the point is, okay, so the reason I emphasize this is the electron domain geometry is because the real geometry of the molecule may or may not be exactly the same, just like this. Okay, so now we need to talk about the variation of the shape, the variation of the shape. So in the following parts, I want you, if you put it in a note, I want you to make a new page and make this page as a landscape shape. Okay, not in the portrait. In the landscape, we need to draw a pretty big table, okay, to identify the different variation of those geometries. Okay, the variation of those geometry. Okay, so first, go with me to draw the. Okay, so I'm going to draw the. You probably need a long table. So the first one is electron domain, number of electron domain. Then is electron domain geometry. Number of electron domain geometry. Then the next one is talk about number of bonding domain. The next one is the number of lone pair. Number of the bonding domain number. Then the next one is the structure, molecule geometry. or you can call it as a molecule shape. What is the shape of the real molecule? Then that's gonna be, let me see what else. Formula. How do we write this kind of formula? Then the next one is the bond angle. The next one is example. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. 8 columns. We're gonna make the 8 columns, but we're gonna have a lot of the lines. Okay, we're gonna have a lot of lines. So please just leave enough space in the empty parts, and we're going to draw those kind of the shape. Okay, so let's take a break. Okay, so let's talk about those in detail. So first of all, let me just explain why the molecular shape is different. Okay, why we have the electron domain. How come those electron domain geometry, the shape cannot be shows the exactly the molecule shape? Okay, so let me just give you an example in the demo over here. Well, so for example, let's first talk about the 3 electron domains. Okay, so this is the, if we have a 3 electron domain, okay, doesn't matter what kind of the bond, okay, so here, when we draw the columns over here, we tell the difference between number of the bonding domain and the number of the lone pairs. So what exactly is a bonding domain? Bonding domain, that means single bond, double bond, and triple bonds. Those are all called the bonding domain. So for example, if we have 3 bonds over here, and if you got 2 single bond and 1 double bonds, it also works. Okay, it also works. And as long as they have a bonding domain, the molecule geometry, the molecule shape will be exactly the same, just like the electron domain. As long as the central atom combined with the around the central atom are all bonds, then the geometry of the molecules exactly the same, just like the lone pairs, the electron domain geometry. The only difference is because the lone pairs. Okay. So for example, if we do not have the double bonds, instead we have a lone pairs, then they make the geometry is completely different. Why? It's because the bonding domain, they have the bonds. They are actually connecting another atoms over there. Okay. So we can see the bonds. Okay. in the real geometry. But for the electron lone pairs, the electron lone pairs is invisible because it's just the electrons. You cannot see it. So although the electron lone pair occupy the space, but the point is you cannot see it. So the leftover parts is just like this. So we have to give it another name. This is not a trigonal planar anymore, right? It's become a band shape. So they become a band shape. So that is why sometimes if you have a lone pairs around the central atom, the geometry of the molecule is different from the electron domain geometry. That makes sense, right? So that is why we have some of the options. Okay, yeah, we have some of the options. So here we're going to talk about some of the options. So first, if we have a 2 electron domain, okay, then generally the electron domain geometry is just a linear, it's a linear shape. And if we have a 2 bonding domain, doesn't matter it's single bond, double bond, or triple bonds. And as long as we have a 2 bonding domain and low lone pairs, and then the shape will be just a linear shape. Okay, so the formula, usually for the formula, we write like this, AX, okay, AX2. The X means the side atoms. Some people would like to write AB2. It's the same thing, okay, AB2, AX2, that's the same thing. It's talk about that this guy has A as a central atom and X as a side atoms, okay, as side atom. And they have 2 side atoms to represent the 2 electron domain, okay? And the bond angle will be 180 degree, right? We talk about if it's a linear shape, they have to be a 180 degree. So that's a linear shape. They have to be 80 degree, okay? So this is a very straightforward. The most common thing is just the CO2, okay? CO2 is a straight line, okay? CO2 is a linear shape. Carbon dioxide, they have a 2 electron domain, only just a 2 electron domain around the carbon, around the central atom, 2 double bonds. So this guy gave us as a linear shape. Well, we're not going to talk about what happened if we have a one bonding domain and 1 lone pairs. This is exactly the same thing. So the demo is just here. So if we have just 1 bond, you see, if we have just 1 bond and 1 lone pair, and the shape is still linear, right? The shape is still linear. So we're not counting this. Generally, there are no such kind of questions, okay, for this. So I'm going to just ignore that part, okay? But you need to know, okay, this is still a linear shape, right? Nothing else. The most common is just HCl or HF, right? They have a lot of. Okay, so then let's talk about 3 electron domain. So if we have a 3 electron domain, the electron domain geometry is a trigonal planar. Trigonal planar. So if we have a 3 bonding domain, no lone pair, well, then that's geometry of the molecule will be exactly the same. It's just a trigonal planar. And for the formula, that's going to be just AX3, 1 central AX3. So in this case, they have 1 atom in the central, and A is a central atom. 3 AX3, the X is a side atom. They have 3 sides. Okay, so they have 3 side atoms. So it's just like this. The bond angle will be just 120. Okay, 120 degree. So trigonal planar, they have the 120 degree. And one of the example is just what we talk about the exception. So that's why when we draw the BF3, the boron trifluoride, we draw something structure like this, because this structure is more close to what it's supposed to be. Okay, yeah. So this is BF3. Okay, the one of the example. So that's a CO2, and this is BF3. Okay. Okay, so and then in this case, you're gonna have the variation. For example, if we have a 2 bonding domain, but if you have a 1 lone pair shows up there, then things will change. It's no more trigonoplanar shape because we are having one of the lone pairs instead of the we have a one of the lone pairs instead of the bond, and then the only thing you can see is a bond. So this become a band shape. Okay, this become a band shape. And if we draw this formula, then this formula will be changed because this guy only have a 2 side atoms. So the X can only just write 2, right? They only have 2 side atoms. You're gonna write AX2. But the point is, if you write AX2, then that can be the exactly same, just like this. So that is why a lot of people writing this as a AX2E. Okay, so the E means electron lone pair. Okay, they try to separate the electron lone pair with the atoms. So they write AX2E. The E means electron lone pair. Okay, so this guy still have a 3 electron domain, but 2 bond and 1 lone pair. And in this case, the bond angle is still around 120, but here I would like to emphasize it's not exactly 120. It's a little bit smaller than 120 because if you look at here, the bond domain usually is smaller than the lone pairs. So the lone pairs usually will occupy the bigger space than the bond, which means I can draw this somewhere else. So if you have central atoms over here, and the bond, the electron lone pairs, since they have 2 electrons, they probably occupy bigger space. And then they kind of like pushing those 2 bonds a little bit inward. And then it's making, originally the bonds should be 120, but since the lone pairs are pushing the bonds a little bit inside, so make this angle is a little bit smaller, 120. You don't have to know exactly what is the degree, but should be a little bit smaller than 120. That makes sense? Okay, yeah. And just to let you know, the more lone pairs, the bigger push for those bond angles. Okay, so if you have a more lone pairs, the bond angle should be even smaller. Okay, so here I can show you one of the example. Let's see. Okay, so this is SO2. This is one of the example. They have 2 bonding domain, 2 double bonds, and 1 lone pairs, as all here. Okay, and then if you see the bond angle is not exactly 120, it's a little bit smaller, okay, but not too much smaller. Okay, so a little bit smaller. This is one of the examples. Okay, yeah. So let's see, SO2. So they have a sulfur inside and have 2 oxygens and 1 lone pairs. Okay, 1 lone pairs. So this guy is one of the example, SO2. Okay, yeah. So the bond angle is smaller than 120, but it's not exactly 120, but smaller than 120. Okay, yeah. So this is the options if we have 3 electron domain. Okay, and then let's talk about if we have 4 electron domain, the geometry will be tetrahedral. Tetrahedral, they have a 4 electron domain. So if we have a 4 bonding domain, no lone pairs, then I said that's going to be the geometry of molecule will be exactly the same, just like the tetrahedral. And then the formula, we're going to just draw AX4, right? Since they have a 4 side atoms, one lone pairs, or one central atom. The bond angle we talk about is 109.5. If there's exactly no bonds, no lone pairs, that's going to be just 109.5. And one of the example is just methane. Okay, methane, CH4. Okay, CH4. So methane will be exactly like this. They have a 1 carbon in the central and 4 side atoms, 4 hydrogen like this. So this guy will be exactly the same. Okay, CH4, that's going to be the tetrahedral shape. Okay, well, then for the 4 electron domain, then they have some of the variation. If we have 3 lone pairs, if we have 3 bonding domain and 1 lone pairs, you add them together, still 4 electron domain. Then let's see what the shape could be. Then one of the example, that's going to be ammonia. So if you look at the ammonia, central atom is nitrogen and the 3 hydrogen, and there's a one lone pairs like this. So that's ammonia. So if you look at here, you can think about, don't think about the top parts. The top part is invisible. So the turns out it becomes something like this. It's just like a tripod, okay? I mean, there's no stick, it's just a tripod, okay? So this is what we give it a name. It's called a trigonopyramidal, okay, trigonopyramidal. So this guy is called a trigonopyramidal. It's called a trigonopyramidal. Okay, trigonopyramidal. It's just like a pyramid, but the base only have 3 lines without not 4 lines. So that's why it's called a trigonopyramidal. Okay. So when we draw this formula, it's just AX3E. So they have 3 side atoms and 1 electron lone pair. So AX3E. And again, the bond angle is smaller than 109.5, right? That should be smaller than 109. Then if you look at the example of here, the bond angle give you is 107.8, right? It's a little bit smaller than, so you can just think about this 107.8 degree, okay? Degree. Example is just ammonia. Let me just say. So that's ammonia and H3. So that's ammonia. And we have one more options. So if we have a 2 bonding domain, and also we have 2 lone pairs, which is 2 bonding domain and 2 lone pairs, then let's see what is geometry of like this. This will be, example will be just the water. Then let's see water. Water, you see, this guy has a hydrogen oxygen in center, and we have a 2 hydrogen, and also water has 2 lone pairs. So remember, when we draw the water molecule, this is what we draw, right? This guy has 2 hydrogen and 2 lone pairs shows over there, and this exactly shows like this. So now, since the 2 lone pairs is invisible, you cannot see that. So make this molecule is in 2D, right? It's not 3D anymore. It becomes 2D. Then this shape is just a band shape. It's a 2D band shape instead of 3D. geometry, it become a 2D geometry. So very important, water is a band shape. It's not a straight line. It's not a 3D. Water is a band-shaped molecules. Okay, so that is the water, and the geometry is just a band shape. It's the band shape. So if we draw the former, it's just AX2 E2. That means they have a 2 side atoms and 2 electron lone pairs. Okay. If you look at the bond angle, this bond angle is even smaller, right? The reason is even smaller, and we talk about is because they have a more electron lone pairs. The more electron lone pairs, the much push to the bond angles, make the bond angles even smaller because the lone pair occupy even bigger space. So they're going to pushing those two bonds become even smaller. So that is why the bond angle here is 104.5. You see, 104.5. And if you realize 1 lone pairs make this, 2 lone pairs even smaller, right? So this is kind of could be one of the examples, one of the questions. They show you, okay, this is a water molecule. They could show you, okay, so between those 3 of the molecules, which one has the smallest bond angle, right? Those guys are all have a 4 electron domain, but this guy water has an even smaller bond angles because this guy has a 2 lone pairs, so pushing those bond even smaller. Okay, yeah. So this could be one of the example. All right, so this is generally we talk about a 2 electron domain, 3 electron domain, 4 electron domain. And you may ask, could be we have a 3 lone pair, if we have just the 1 bonding angle, and don't write this, okay? And we have a 3 lone pairs, that could be, but the shape is just a linear. So usually we don't write this. For example, let's just go back to look at this. So if we have a 3 lone pairs, you see, they have a 3 lone pairs like this, and there's only just 1 bond, and the make it turns out it's just a linear shape. So usually we don't do this, okay? Yeah, so I just exclude this out of the chart, okay? Because that's gonna be very, very obvious. I mean, one of the example is just a HCl. You see, HCl, this guy, the chlorine has a 4 electron domain, but they have a 3 lone pairs, 1 dash. So this guy is going to be a linear shape. Make sense, right? Yeah, makes sense, right? So I'm going to just include that. We don't talk about this guy. All right, so let's keep on. Okay, so if we have a 5 electron domain, okay, 5 electron domain, we give its name, it's called the trigonal bipyramidal. This one is a pretty long name. Trigonal bi, not the trigonal pyramidal. Trigonal pyramidal is over here. This is trigonal bipyramidal because they have a 2 pyramid. Okay, trigonal bipyramidal. So if we have a 5 bonding domain, no lone pairs, then that's going to be exactly the same. It's just a trigonal bipyramidal. Then we just draw AX5. They have 5 atoms around it, AX5. So the bond angle will be special. So we can look at one of the examples. The AX5. Oh, let's see. No, not this one. PCL5. Okay, PCL5. This is one of the example. Then you will see phosphor is in the central, and then they are going to have 5 chlorine on the side. And then if you look at the bond angle, this is there's a lot of combination with a bond angle. They have a 90 degree, which is the straight line that we have a 90 degree over here. And also if you count this angle and this angle, 90 degree plus 90 degree, we have a 180 degree, right? And if you if you look at from the top, this is you look at from the top, the bird eye vision view, and then you will see you also has a 120 between those 3 atoms, right? So they have a lot of combination over here. And the bond angle, this one is special. They have a 180 degree. They also has a 90 degree. And also they have a 120 degree, okay? So this one is special. Usually we're not testing this, okay? One of the example is just a PCl5. Okay, phosphor in the center, and we have 5 of chlorine. Okay, so in this case, we don't have enough space, so I'm not going to draw the dots. But suppose you're going to draw the dots around it to make a correct Lewis structure, okay? So next one, so what if we have a 4 electron domain? Sorry, not 4 yet, 4 bonding domain, but we have a 1 lone pairs over here. Then they are going to missing one of the electrons, one of the dots, okay? Then let's see what is the geometry of these molecules. Is SF4, okay, SF4. This guy, you see, this suppose has a 4 electron domain. They have a 4 bonding domain and 1 lone pairs. The lone pairs is invisible, and we can give its name. It's called a seesaw. Can you tell why this is called a seesaw? Okay, seesaw, okay, yeah. So that is why we give its name called a seesaw. And you can see the bond angle is a little bit smaller than 90 degree, right? It's because this lone pairs is pushing those down. So this angles shouldn't, is a little bit smaller than 90 degree. That makes sense, right? Okay, so let's see. We give its name, it's called a seesaw. And the formula is just AX4E. Still 5 electron domain, but they have a 4 bonding domain and 1 lone pair, okay? So the angle is smaller than 90 degrees. One example, just SF4, okay? SF4. So you have a sulfur in the middle, and you have a 4 sulfur. So this is a SF4, okay? And we can also have a 3 bonding domain and 2 lone pairs, okay? Which means we're going to missing another bond. And this structure, one of the example is something CF3, okay? This guy still have a 2 bonding, and if you raise up, it should looking like this, okay? This give us another name, is called a T shape. You see, this guy looks like a T, right? It's called a T-shaped structure. This is called a T-shaped. It's a T-shaped structure. The former is just AX3, since they have 3 side atoms and 2 lone pairs. And if you look at the bond angle, then again, this bond angle still smaller than 90 degree, but it is even smaller, should be even smaller. Again, still smaller than 90 degree. Okay, I guess probably when we talk about bond angle, they're not going to do those complicated structure. Most of the case, they're going to test the 3 electron domain and testing your bond angles. Okay, to compare the bond angle between each others. Example is a CF3. So you have Cl, and you have fluorine on the side, and the 2 lone pairs. Okay, the last case, if you have a 2 electron domain, a 2 bonding domain, but you have a 3 lone pairs, then what is the shape? Okay, this guy will become exactly just a linear shape. Xenon F2. You see, they losing everything in the middle. They lose everything in the middle. You see, they lose everything in the middle, and then since this guy has a three invisible lone pairs over there, they cancel to each other. The push against to each others. So then it turns out the bond angle, the bond is not going to bend. The bond is not going to bend. Then they're going to be a straight line because the 3 lone pairs actually is against to each others. They cancel out the force between each other. So they are still going to become a linear shape. It's just a straight line. Interesting, right? Yeah. So this is just a linear shape. And we'll just draw AX2, E3. So 3 electron domain, 3 lone pairs, electron lone pairs. The bond angle not smaller than 90 degrees is exactly is 180. And the one of the example is just xenon F2. This guy xenon has 3 electron domain, 3 lone pairs up there. So XeF2. Okay. Well, let's take a break, and then we will talk about the last shape. The last shape actually is easier than this one. Okay, so the last part. Terrible line. Okay, so now if we have a 6 electron domain, then this is called the octahedral. Obviously, if we have a 6 bond and a bonding domain, no lone pairs, they are still going to call it octahedral. And then the formula is just AX6, since this guy has 6 atoms around it. The bond angle is exactly 90 degrees. Okay, exactly 90 degrees. One of the example, just let's see, SF6. So if you see this guy, you see everything is identical. This whole molecule is identical. Doesn't matter how you rotate, they always exactly the same. Okay, yeah. So the bond angle is just 90 degrees. And the example is just SF6. Okay, yeah, I'm not going to draw the structure. It's pretty complicated. So if we have a 5 bonding domain and only just one lone pair, then we give its name is called it's a pyramid. Okay, something 5, BR5. You see, this guy is called a square pyramidal. The reason it's called square, which means this one is just like the pyramid in Egypt. Okay, it's a pyramid like in Egypt. A little bit difference because since this guy has a lone pair on the top, so they're pushing the angle a little bit down, getting a little bit smaller. But this is what we call the square pyramidal. The bottom part has a square, so that's called a square pyramidal. Okay, it's called a square pyramidal. And just to let you know, those are all not nature molecules. Those are all man-made molecules. Okay, yeah. Square pyramidal. Okay, we're just writing AX5E since they have 5 atoms, only 1 electron lone pair. The bond angle is a little bit smaller than 90 degrees, and one of the example is BRF5. Okay, BRF5. Let's see. We have one dot shows. So that is called a square pyramidal. The last geometry is 4 electron domain and 2 lone pairs. Okay, 4 bonding domain. If we have 4 bonds and only 2 lone pairs, then that's gonna be exactly just a square. Okay, so exactly a square, just like this. Okay, and we call this is a square planar because those are all 5 atoms in the same plane. And since those are 2 lone pairs cancel to each other, so make the bond angle exactly as 90 degrees. It's canceled. Okay, so this is one the example. It's called square planar. It's AX4E2. Okay, the 90 degree exactly equal to 90 degree. One example is just XeF4. So we have a central atom, Xe in the side. Let me just. For fluorine on the side. Okay, so that is exactly the shape for the square planar, and that's it. Okay, so if we have a 6 electron domain, that's probably is the structure. I don't think so. I don't think we have, if we have 3 lone pair and a 3 electron domain, usually we don't have this shape. Usually we don't talk about this kind of shape. Okay, although this is called T shape, but usually I don't talk about this shape. So generally, this is the pretty much the topic we're talking about for the geometry. Then let's talk about how do we use this table. I'm just writing the table for you, right? But if I give you a formula, how do you determine based on this to determine a formula, right? For example, let's just any of the compound you have, think about one of the chemicals, and then we can determine what is the geometry of this molecule. Anything? Phosphate. Okay, phosphate phosphate is not a compound. Phosphate is a polyatomic ion. Although they have a shape, but I don't want to talk about that one over here. So let me just give you one example. Okay, so majorly we're talking about is the geometry for the molecular compound. Do you see that? All of those molecules are molecular compound, right? We didn't talk about something else. Well, if you're talking about the phosphate, that's okay. Yeah, we talk about the phosphate. Okay, a lot of people, they write a geometry like this. Okay, so if you look at this is a phosphate, the Lewis structures. Well, then what do you need to do? You need to look at the central atom. Central atom, around the central atom, how many electron domain they have? 4, right? Any lone pairs? No, only 4 bonds over here. So they have 4 electron domain. So you see, this guy has a 4 electron domain, right? This guy has 4 electron domain. All of the domain is 4 bonds, no lone pairs. And it turns out the geometry of this molecule for the phosphate is a tetrahedral. Okay, it's a tetrahedral. Make sense? Okay. Okay, so how about the next one? Okay, let's say SO3. Okay, we talk about the SO3 molecules. The geometry is S, and they have 1 double bonds, 1 single bonds, and 2 single bonds shows up there. So that is the geometry, the Lewis structure for the SO3. Then what do you do? Look at the central atom. How many electron domain they have? 1, 2, 3. This guy has 3 electron domain. Okay, any lone pairs? No lone pairs. So they give, based on the table, then we need to go side. Okay, so this guy has a 3 electron domain, 3 bonding domain, low lone pairs. And give us a geometry is just the trigonoplanar for this molecule. Okay, so that is why we draw this like this. It's trigonoplanar. Okay, yeah. Well, so let's just make the short version. So how about the carbon? If we just give you conceptually for this compound, for this central atom, what kind of geometry for this carbon? It's just a linear, right? Because they have only 2 electron domain, and that's a linear. So if we have a carbon, we have one lone pair and two single bond. Then what kind of geometry for this molecule? Trigonoplanar, right? Because they have a low lone pairs over here. That makes sense, right? And they have 3 electron domain, non-lone pair, so trigonoplanar. Well, if this carbon has 4 bonds over there, what kind of geometry could it be? Tetrahedral, right? Because the central atom has 4 bonds, no lone pairs. That's it. Yes.
Butane.
Butane. Okay, butane is complicated. Let's see. Okay, butane is a C3. No, butane. Butane is a C4, C4H10. Okay, so this guy is complicated. They have 4 carbons. Okay, you cannot just based on this to making structures. So propane, you can draw the propane. Propane 3 carbons. They have 3 carbons. Okay, this is a C3H8. So you have a carbon over here. This guy is actually containing 3. Sorry. This is the Lewis structure for the propane. Well, if you're not counted on this, if you're just looking at the central atom, this carbon, what is the geometry for this molecule? Okay. Well, I forgot to do 2 lone pairs over here. So if you look at over here, this guy will have, oh, sorry. I shouldn't. This, there's one more hydrogen in over here. There's one more hydrogen. So in the central atom here, they have 4 bonds, which means they have 4 electron domain. So they gave you the geometry should be like the tetrahedral shape. But obviously, there's a 2 side is really, really big, but there's another side is really, really small. Okay, yeah. So that is why when we talk about the geometry, we only talk about the 2 atoms combined together. That's make it much more easy to recognize. Okay, yeah. So let's see. How about the CO2? How about CO? Carbon hydroxide. We draw the carbon monoxide. The geometry of this is this. So what is the shape for this guy? Obviously, it's a linear, right? If you look at this carbon, there's only 2 electron domain. So as long as only just 2 electron domain, they always is a linear. It's just 2 lines. You see, only 2 atoms combined together. Doesn't matter how they form, they always is a linear shape. That makes sense, right? Yeah. Okay, yeah. So this is how we use this table. Based on the Lewis structure, look at the central atom, and based on the central atom, it determines what is the geometry of these molecules. Okay, and you see what is the total electron domain they have, how many bonding domain they have, how many electrons they have, and then you give your what is the geometry of these molecules. Make sense, right? Okay, so this is pretty much we talk about for the how to use the geometry of the molecules. And I would like to spend the last several minutes talk about the polarity of the molecule, right? We talk about the polarity. We talk about the polarity of the bond. But for the molecule, they also could have the polarity of the molecule. The polarity of the molecule, for example, for the carbon, methane, okay? So methane, this guy is so identical. Doesn't matter how you rotate this guy, they always exactly those guys is so identical for each other's. Doesn't matter how you rotate, this force is always identical, right? So it's a very symmetric. So for this kind of molecules, although we know there's a bonds, the electron activity, for example, the carbon is going to pulling the electrons towards into center. But the point is, since they have four hydrogens, those fours all cancel to each other. In another word, the electrons will distribute homogeneously or the equally for all the atoms, right? So in this case, this guy is non-polar. It's a non-polar molecule, right? As long as the electrons distribute evenly, then they give you non-polar molecules, okay? There's no trends. But if you're, this is one example. Well, if you're talking about the CCl4, I mean, that's the same thing, right? CCl4, that's the same thing, okay? Yeah, those are canceled to each others. And if you're talking about carbon dioxide, this is also carbon dioxide. This guy is identical, right? Yeah, this guy is identical, right? So although oxygen is going to pulling the electron this way, this oxygen is pulling the electron this way, but overall, there's no end. If you're consider this guy as a whole molecule like this end and this end, they're not going to have any of the charge because those force is pushing canceled each other's. Okay, so this is also a non-polar molecules. So the conclusion is, if you see a molecule, this is a very symmetric. Okay, every side is symmetric. For sure, this molecule is a non-polar molecule. They're not going to have any of the polarity shows over there. Okay, now what kind of molecule is a polar molecule? Then you can see, for example, it's just oxygen, the water. Water is like this, right? We talk about the water is a band. So why the water is a polar molecule? Then you can think about oxygen has a stronger electron activity than the hydrogen. It shows the power. So they're going to pull in electron over here. This way, they're going to pull in the electron this way. So does that mean they're going to have a more dominant electrons on this side, but we have a less dominant electrons on the hydrogen side? So make this has a stronger dipole moment trend. If you look at this guy as a whole molecules, and on the bottom side, they have a partial positive, but on the top part, they have a partial negative. So that is why they're making the water molecule is a polar molecule. This guy have a dipole moment. They give us this molecule is a polar molecule. Yeah, the reason is because this guy, there's no force that cancel the top parts. So make it this, the top part is more dominant with the negative charge, and the bottom parts more dominant with the positive charge. Are you with me? Okay, so water is a very typical polar molecule. And if you're talking about ammonia, it's doing the same, right? The geometry of the ammonia is something like that. This is the geometry of the ammonia. They have a lone pairs on the top. And you can see ammonia, again, is going to grab the electrons, pulling electrons to this side, and also pulling electron this side, pulling the electron this side. Overall, there's going to be more electrons dominate to the ammonia side, but we have a less hydrogen, less electrons dominate in the hydrogen side. So if you look at the 3D geometry, and they're going to have a trend. The top ammonia side, they have a more partial negative, but for the hydrogen side, they have a more partial positive. So that's why ammonia is also a polar molecule. And you can see ammonia is not an identical molecule. It's not a symmetric molecule. Water is not a symmetric. I mean, symmetric, we talk about, it's not a mirror symmetric. It's talk about the center symmetric. Okay, let's talk about center symmetric. So generally, this is the polar and the non-polar. Why we talk about polar and non-polar? That's because there's a, okay, so we talk about the solvation or the dissolution, okay? Polar molecule can only dissolve in the polar solvent. Non-polar molecule can only dissolve non-polar solvent. So polar molecule cannot dissolve in non-polar solvent. Non-polar molecule cannot dissolve in the polar solvent. Okay, so so that's why we call this a like dissolves like. Okay, dislike cannot dissolve dislike. Okay, so that is why, okay, since the water is a very universal solvent, right? And have you heard if you buy the paint, have you heard it's called a water-based and oil-based? Okay, yeah, the oil in general, those are non-polar molecules. Most of the oil are non-polar molecule, or water is a polar molecule. So that's why the oil cannot dissolve in the water because one is a non-polar, one is a polar, okay? And those one that can dissolve in the water, most of the case is a polar molecules. And there's a joke for chemistry here. So what kind of bear cannot swim? Polar bear. Why? Because it's a polar. When they swim, it will dissolve in the water. Okay. Yeah. So hopefully you can remember this. Okay. Polar dissolve polar. Non-polar dissolve non-polar. Okay. So those are quite different things. So that's why we call the like dissolves like. Unlike dissolves unlike. Okay. Yeah. So this is pretty much I'm going to talk for today. And let's just pack things and we will move to the lab.